Ray Schneider says, so how come Uranus is on its side, and how does this stuff about craters work to tell the age of things? Two good questions. Uranus is on its side. There's some suspicion that because Uranus has some very unusual properties to it, it's the third gas giant. Jupiter, Saturn, Uranus, and Neptune. Jupiter's gigantic, Saturn somewhat smaller. Uranus and Neptune are both relatively small. There are only 3 or 4 Earths across. If you put Uranus next to the Earth, it just looks like, big planet, but not big in the same way Jupiter is. But Uranus is unusual because it's lying on its side. And it doesn't mean that one pole is always facing to the Earth. It means that one pole is always facing in a certain direction in space, and as it orbits the Earth, there are times when the North Pole is facing the Sun and times when the South Pole is facing the Sun. It's got a very long orbital period. Somebody will tell me what it is. I don't remember now, but it's got to be in the order of about, 50, 60 years, something like that. Saturn's 30-ish. So 24, 27 for Saturn, something like that. So it's usually doubles on the way out. Nobody really knows why Uranus is on its side. There's some evidence that Pluto, there used to be believed that Pluto was a moon of Uranus that was kicked out by whatever caused Uranus to go over. Almost certainly was caused by the close approach of a large body of gravitational body from outside the solar system. However, one of the things that I've heard, and I want to get to this a little later with the moon thing, is that it is not that any spinning body, like the Earth or Mars or anything like that, has a relatively stable sort of a spin, and over long periods of time we know that the Earth's axis precesses. That's where I think it's about a 23,000-year cycle where the Earth's pole points to different parts of the sky. Right now the Earth's pole is pointing towards a faint star called Polaris, second or third magnitude star called Polaris, which is the pole star. But over the course of thousands and thousands of years, that axis wobbles, so the night sky no longer turns around Polaris. It turns around blank places in the sky and comes fairly close to Vega, which is a very bright star, 5th brightest star. But nothing is as close to the circle of potential north celestial poles. The north celestial pole is what the Earth rotates around. The Earth spins on its axis, so the sky appears to rotate around a point that doesn't move, and that point is where the Earth's axis is projected out to. That's the north celestial pole. It's just a point in the sky. Because the Earth wobbles and precesses over the space of, I want to say, about 23,000, 26,000 years, that point moves in a circle, and then it comes back to the same spot again. Interesting coincidence for us is that even though Polaris is not the brightest star on that circle, Vega is much brighter. Polaris is the closest star to lie on the circle. It's only about a degree off. And furthermore, right now, the North Celestial Pole is as close to Polaris as it possibly could be. So as years go on, the North Star is going to get further and further away from the North Celestial Pole. It'll be a little less useful. Eventually, it'll be useless. Why do I bring all that up? Well, because in addition to the Earth's rotation, which happens every 24 hours, the Earth's orbit, which happens every 365 days, the precession of the Earth, like a spinning top of the axis moving around, which happens every 26,000 years, 23,000 years, something like that. There is some evidence that says that spinning bodies like this will eventually flip over, that they will flip over. I've heard evidence that says that Mars once was flipped over, that all of them eventually flip over time. And the flip doesn't take very long in terms of the length of the total cycle, but it happens. I don't know if that's true or not, but somebody said that one of the reasons that the moon is so important to Earth's life is that the moon gives the orbit of the moon helps to arrest this. Now, if it turns out that this polar flip is just part of the nature of spinning bodies, then you can see how, without the moon, life on Earth would still exist, but intelligent life likely not. Certainly technologically life likely not, because the planet flipping over on its side, which takes thousands of years, is a catastrophe. It's a catastrophe not because everything just slides off into earthquakes. It's a catastrophe because if for the space of 2,000 or 3,000 years, while the planet is lying on its side, half of the year the North Pole is facing towards the sun and the other half of the year the South Pole is facing towards the sun, it means that virtually the entire planet is cooking for 6 months out of the year and freezing for 6 months, another half of the year, and that knocks a lot of life off the table. It just resets the clock. You go back to zero, and you start with your, with your algae and your mosses, and you just, all right, here we go again. Now, we've had a number of extinction level events on planet Earth, but if something like this is regular, then you could see why there aren't so many intelligent species in the world or in the universe. But if the moon helps to inhibit that, then once again, it's the presence of the moon. It's the moon that makes Earth unique for intelligent life. If anybody has any information on that, I'd love to hear it. So I don't know what caused Uranus to go over on its side. I do know that it's the only planet currently on its side. Those of you who say, well, this can't be possible, might have to explain why Venus rotates backwards. All other planets looking down from the North Pole appear to rotate counterclockwise. Is that right? Yes. Looking down from the top, Venus rotates clockwise, the only planet that does that. And slowly, 260 days, all this stuff's coming from the top of my head, but something like that. So, any kind of long-term, long-cycle irregularities that cook half the planet and freeze half the other are not conducive to intelligent life. It's very hard to kill all the life on Earth, but it's possible to kill the big life forms fairly easily, and asteroids will do that. And if this planet keeps falling over on its side, well, that's another case for why we're unusual. The moon helps. The moon, of course, is Earth's a double planet. The moon is stabilizing, and we talked in the first episode about how the moon protects us against so many asteroid impacts, just knocks them out. It takes some, it just literally blocks them as a shield, and others it simply accelerates out or in, and it's amazing really how wonderful that moon is, and I want to come back to the moon when we get to that question, I think. But the other part of your question I think is kind of interesting, and this one I actually can answer, and answer relatively simply. How does this stuff about craters work to tell the age of things? That actually works fairly simply. The more craters that an object has, the older it is. And it's pretty simple really to understand. Most of the cratering that took place in the solar system happened during the first billion years or so of the solar system as the solar system was assembling itself. In other words, in the early days of the solar system, the planets were still molten. There were literally billions and billions of large objects. And they're all in motion, and basically what's happening during the first billion or so years of the solar system is the planets are aggregating. More and more objects are impacting the surface of these protoplanets, making them bigger, and the bigger they get, the more gravity they have. The more gravity they have, the more they pull in more of this junk, and they're basically vacuuming out space. Space is amazingly empty. You see things like the asteroid. This is another one of these things we talked about last episode, how if you look at the solar system, the planets all look so big, but they're incredibly small compared to the sun, and they're incredibly spaced out. And you see the asteroid belt, and it's a series of dots, and hundreds and hundreds and hundreds of asteroids in the asteroid belt. Well, as it turns out, there's hundreds of thousands, if not millions of asteroids in the asteroid belt, but they're so tiny and so spaced out that you'd never see them. You go through the asteroid belt, you can go back and forth through the asteroid belt for the rest of your life and never see an asteroid, never come near an asteroid. They're incredibly empty. And one of the reasons the solar system is so empty is because virtually all of the good stuff has already hit something. Now, Jupiter, for example, is the solar system's vacuum cleaner. Without Jupiter, we'd be taking impacts today, massive impacts. Jupiter's gravity is so enormous that Jupiter's just swept up a bunch of the stuff that would have kept hitting Earth and kept resetting the intelligence clock, the life clock. Some big old thing that was meant for Earth got sucked up by Jupiter. Some of them are still in place around Jupiter. Those of you who are really into this kind of thing know that there are stable gravitational positions called Lagrange points, and some of them precede Jupiter by its orbital diameter, and some of them trail Jupiter by its orbital diameter. They're called the Trojans and the... what's the other one? I forget. But basically, there's clusters of asteroids moving in front of Jupiter, clusters of asteroids moving in back of Jupiter, and likewise for the Earth and the other planets. So, the answer to your question here with a cratering, Ray, is this. If you look at the moon's a perfect example. If you look at the surface of the moon, you'll find that parts of the moon are very heavily cratered, and they're light in color. And other parts of the moon are much, much less heavily cratered, and they're darker in color. Now, sometimes one of these most brilliant craters, like Tycho, sorry, not Tycho, Copernicus, on the moon will make an incredible impression because it's on a very dark, relatively flat, smooth plane, and there's this brilliant white crater with all the rays of ejecta that's spread out over the surface of the moon. Now, the reason we know that this makes perfect sense. The reason we know that the lunar lowlands, the Maria, the dark areas, are younger than the other areas because there's fewer craters on them. So the way to think about this is this. Here sits the proto-moon, and finally the moon cools to the degree where the surface is no longer molten, which means that a crater can form and survive. It's getting hit all the time, and it's just getting so cratered, and pretty soon we have saturation on the moon. Mercury's saturated. Virtually all the objects in the solar system that don't have atmospheres are saturated. Enceladus is saturated. All the moons of Saturn are saturated. What that means is you cannot put a crater down without destroying pre-existing craters. They're just literally nothing but craters. The more the craters, the older the object is because they've been taking craters for a longer period of time. The reason that the dark areas on the moon are not as cratered is because much more recently than the big asteroid impacts that caused most of the cratering, some very large impacts flooded the surface of the moon with basalt from down below. And so basically, if you look at the gigantic lunar seas, most of them are arcs. They're enormous impact craters, absolutely spectacularly large, from objects that were so big that they not only wiped out the other existing craters, they caused, magma to seep up from the surface of the still molten moon. And because this is young, all of this lava came up and it basically solidified and made a nice, dark, smooth surface. Now, onto that, since the formation, which happened later than most of the cratering, the amount of cratering goes down with time because most of the objects have been cleaned up and hit things. Every now and then, there's a crater on a dark floor of the Maria. The more craters there are, the longer it's been exposed to cratering. The fewer craters there are, the less time it's been exposed to cratering. So anytime you see a smooth surface in the solar system, you know that surface is relatively new. Relatively new is billions of years. The reason there are so few visible craters on Earth is because Earth, unlike Mars, unlike Venus, really unique among the terrestrial planets, the hard planets, Earth still has a molten core, and Earth has plate tectonics, which means that over long periods of time to us, but relatively short periods of time in the life of the solar system, parts of the Earth crust get subducted underneath other parts, and other parts continue to grow. The Atlantic Ocean is getting wider. Right at the mid-Atlantic ridge, the Earth is coming apart. New materials being pushed out, and old materials going under. And that means that the surface of the Earth is constantly being resurfaced. So there's a couple reasons why there are so few craters visible on Earth. There's a few. Barringer Meteor Crater is a small one. You can occasionally see round lakes or circular lakes as the result of impacts. There's a big impact crater underneath the Gulf of Mexico, which was the Yucatan impact that wiped out the dinosaurs last time. But basically, there's very few craters on Earth, and there's several reasons for this. One of the reasons is because the Earth has an atmosphere that breaks up incoming large objects into smaller objects. Tunguska was a pretty good example, and for those of you who saw that giant Russian meteor from 2-3 years ago, basically asteroids are not solid rock. Most of them are rubble piles. And if something like an asteroid or a comet, which consists of a lot of mass but not terribly tightly held together, as this stuff hits the atmosphere, especially if it's at an angle where it's got more atmosphere to go through, it'll break up into little pieces, and these little pieces will knock down trees and stuff, but they won't scoop out a big old crater. So one of the reasons the Earth doesn't have a lot of craters is because the atmosphere protects us from certain types of impacts. The second reason that we have fewer visible craters is because of weather. The fact that it rains and that wind blows and that that sediments are deposited by rivers and stuff covers up craters that have actually formed on the Earth. And over a very long period of time, the craters that had been on the proto-Earth basically just got subducted into the crust along with everything else over the course of time. And as new material came out, which is newer, the new material that makes up the current surface of the Earth is post-peak cratering material. It's not to say that impacts don't still happen, but, the Earth's about 4.6 billion years old, and if you'd been around 4 billion years ago, this stuff would be coming down hither and yon, just would have been cool. One of the things I hope to see, so, the chances are extremely small, very small, but not zero. I want to say back in the early 90s, I think it was, Comet Shoemaker-Levy, there was an a comet that passed very close to Jupiter, very close. It came so close to Jupiter that Jupiter's gravity tore it into shreds, into pieces, broke it up into several different pieces. And as the two orbits got into a certain resonance, they realized that Jupiter and this comet are going to be in the same place at the same time again several years from now or whatever, and this will be back in 93. And that large pieces of a large comet were going to hit Jupiter in front of our eyes. And not only in front of our eyes, we actually had a probe either. I can't remember whether we had a probe in orbit or whether it was on its way, Galileo. But it must have been on its way because we don't have any pictures of the actual impact. But anyway, several years ago, back in the 90s, I want to say it was 93, I'm not sure. We knew that a comet and Jupiter were going to be in the same place. And sure enough, even though the comet hit on the far side of Jupiter, very quickly, Jupiter spins every, it was about 11 or 12 hours, I guess, 10 hours, something like that. As the planet rotated, you could see these scars where these enormous enormous comets had hit Jupiter, releasing hundreds, if not thousands or millions of megatons of energy, just enormous explosions. And in infrared, you could see the plume from around the planet. You could see the plume of hot gas being blown out into space by these comets hitting Jupiter. Now, I don't want to see that hit the Earth, needless to say, but one of the things I would like to see that I think would just be cool to see, and we have the means to at least give me some warning, is I would like to see a significant meteor impact on the moon. I think that would be cool. An asteroid or meteor impact. I think it'd be cool if you said, yep, at 2:45 in the morning on 29th of November, 2023, asteroid 1962, which is not very big, maybe 200-300 feet across, is going to impact somewhere in Oceanus Procellarum, and get ready. And then I think it'd be a heck of a thing to see. It'd be a blinding white flash, and this glowing ejecta would come out. Ejecta. I keep saying ejecta. That was the name of my fictional land in the days of eject. This glowing ejecta would come out, and a lot of it would fall back to the moon, and it would lay this white kind of brand new rays on the moon. It wouldn't have to be a super big impact either, by the way. Small is fine for me. And presumably, if it was big enough and hard enough, a period of a week or two would go by, and then all of a sudden we would start to get incredible showers of meteors that wouldn't be composed of regular meteors, iron meteors or carbonaceous chondrites, stony meteors. We would start to see enormous meteor showers for days or weeks or months, and they'd be of molten glass, and they'd be of silicates that had been ejected from lunar gravity by this impact, molten, glowing red hot, cooled down back to black glass like obsidian, and then some of them would be caught in the Earth's gravitational field and then come into our atmosphere. So you'd have these incredible light show on the moon. That'd be cool. That'd be really cool. And you'd have this glowing pattern of ejecta. That would be cool. And then over time, the stuff would come into the Earth's atmosphere, and as it came into the Earth's atmosphere, then you'd get these incredible meteor showers. And these things are called tektites. And tektites are found all over the Earth, but they're found in patterns, and they're found at certain times. And tektites are glass fragments. They're actually moon rocks. We suspected it for a long time, but we had moon rocks on the Earth since there's been humans. And they're little glass particles. Sometimes they're little tiny little things about that big. And it's, pieces of the moon that were blown off of the moon by impacts and then ended up in Earth, went through the Earth's atmosphere, re-entered, and landed on the moon, on the Earth. And somebody knows how to do this. I certainly don't, but there's a couple of, we have Mars rocks on the moon too. There's a couple of meteorites, I should say, that have landed on the Earth that are chemically proven to have come from Mars. So there are Mars rocks on the Earth. By the way, for those of you who are keeping score and maybe want a program to take with you, there are 3 different classifications of that term meteor, and I occasionally, through laziness, get them wrong, but I do know the difference, so here they are. A small object in space, smaller than an asteroid, a small object, a rock, size of a football, something like that. It is called a meteoroid. It's a meteoroid. And as long as it remains in space, it's a meteoroid. The word meteor actually just refers to the flash. So technically speaking, meteors do not land on Earth. Once it's landed on Earth, it's a meteorite. So it's a meteoroid in space. The flash of light we see is the actual meteor. And once it's down on the ground, it's a meteorite. Just thought you might want to know that. So meteors do not land on Earth. No one's ever been struck by a meteor. One person, at least one, maybe more, have been struck by meteorites. No one's ever been struck by a meteoroid. But you could be in outer space, in the space station, be struck by a meteoroid, and you might be struck by a meteorite, but you will never be struck by a meteor. There now, got that all settled. Moving on.